We're going to use this simulation to verify Newton's second law, F equals ma. I've created a spreadsheet for you to record your data. When we run the lab, we get this data here, the position versus elapsed time. And we're going to use that data in the spreadsheet to create a position versus time squared graph, and I'll explain why we do that. If we look at our second motion equation, we've got displacement equals initial velocity times time plus half acceleration times time squared. So the cart starts moving from an initial velocity of 0, so we can eliminate that and we're left with half at squared. So looking at this, we've got position or displacement is, we can say, directly proportional to t squared. So that means if we produce a graph of t squared versus position, we will get a straight line. And when we look at this formula here, the straight line should be half of acceleration. So gradient will equal a over 2. So that means we can calculate acceleration from the position time graph, which we haven't actually looked at previously. And so we'll get acceleration is 2 times the gradient. Okay, so based on that, that's why we collect the data here from the simulation and plot the position versus t squared, use the gradient to calculate the acceleration, and then we can plot our acceleration versus net force graph, which we get here. Okay, and then using the gradient of the acceleration versus net force graph, we get a gradient is 1 over the mass, and then from that we can calculate the mass, and then we can compare the mass to the actual mass that we measured. So we want a constant mass, and that gets measured, so that's the total moving mass of the cart plus the hanging mass. So we can compare the gradient, and if it's close, we know we've got an accurate result. Anyway, so I'll go through and demonstrate how to complete the blank one, and then you can do your analysis. So we're going to do 2 investigations, so I'll take you through how to use the simulation to collect that data. Okay, so I'll reset the simulation, go to the masses, and we're going to start with the hover puck, or well, this is equivalent to our trolley with mass on it. So we'll start with 900, and we'll start with a hanging mass of 100. So just remember, we've got to convert those into kilograms, so it'll be 0.9 kilograms and 0.1 kilogram for this one. So the total moving mass is the sum of these two. So you have to remember to do that. So we'll go back. Actually, let's record the data. So we've got the puck mass is 0.9 of a kilogram, and the hanging mass is 0.1. So that gives us a constant mass. So we've got to make sure when we increase the hanging mass to increase the net force that we start to reduce the same amount off the puck mass as we go. So I'll probably do 2. So this calculates the net force, which is going to increase. Okay, so let's run that simulation and start. and then we record this data into the table. So I'll do that quickly. Okay, so we've got the graph. It'll plot automatically. It will give us the equation. So we know from the equation, as I discussed, that the gradient is acceleration over 2. So if we plug that gradient in here, so 0.491, then the acceleration is calculated here. It's 2 times the gradient. Okay, so we get an acceleration of 0.98. Okay, so this data should get recorded down here in this table here. So that would automatically build that table and plot this graph as you go. Okay, so that's what you need to do there. Then if I go back to this completed one, that's got all the completed data. We've got the gradient, so then you just need to type the gradient into the blank here. This will automatically put in the calculated mass, the one that we've measured initially, and it does the, sorry, I've just changed that. So the experimental mass is the inverse of the gradient, so 1 over the gradient. And we compare that to the measured mass. So that's that mass constant that we keep constant, the total moving mass, which includes the trolley plus the hanging mass. So we compare it, and then it does a percentage difference. Okay, so that's the first investigation. The second one involves plotting acceleration versus an increasing mass. Okay, so in that case, what we need to do is reset, go to the masses. This time you're going to have we'll start with a hanging mass of 500, and that's going to stay constant. Okay, so that's going to stay constant. We will have the puck increase, we'll start from 100 grams. Okay, and then you're going to just increase the puck mass. So, and keep the hanging mass constant. Okay, so you're going to increase the puck mass and keep that constant. So you will get an increasing moving mass. Okay, so we'll run the first one. Okay, and then you plug that data into the table, the same as before. So if I enter, okay, what did I say? The puck will start at 0.1 of a kilogram. That stays constant. So all the way down, you want this to be constant in this investigation, and just increase the puck by 0.2 each time, 0.1 each time. Okay, plot the graph, get the gradient, it'll calculate the acceleration, and then it'll plot it down here, and same process. But in this case, we've got acceleration versus the inverse of mass, or 1 over mass. So the gradient, as we discussed in class, is equal to mass times acceleration, which is the net force. So the gradient of this graph will give us the net force. The expected net force is constant, so it will be taken off here. So 4.9 is what this one should be. Okay,